My name is Caleb Fassett. I'm a senior scientist at the Applied Physics Lab in Laurel, Maryland. It's part of Johns Hopkins University. I'm like a classic case of somebody who's been interested in science and space since I was in elementary school. I have a little report that I did for kindergarten where it was like Apollo and it had the eagle and it was like all things. I come from the generation immediately following Apollo, so we hadn't been to the moon in a while, but I was always into the planets and space and science. My dad is a scientist, so I had a lot of it in the house, and I had some really great teachers. So I've been into it for the whole time I was growing up until now. My educational background is that I went to a liberal arts college, a small liberal arts college called Williams College in Western Mass. That was a really great experience for training me to be a planetary scientist because it gave me a good firm grounding in the whole range of science and writing and all the things you need to do to become a successful scientist. After that, I was a legal secretary for a short period of time, which also helped prepare me to write and communicate. And then I went to graduate school because it turned out I didn't want to be a lawyer after seeing what lawyers do for a living. And ever since I've been just deep in the data analysis from spacecraft that have been exploring the whole solar system, from Mars to Mercury to the moon to Venus to asteroids. So pretty much across the inner solar system. I have not done much professional work on Venus. It's kind of funny, but in college I got extremely excited by Magellan. Had it happened, a year or two before I was taking classes on planetary science, and so I remember the JGR volumes. The things came in books back then. That had the results of the Magellan mission, and just reading them. And the truth is, like, there's been work done since then, right? But not a whole lot of data of the type that I'm interested in about the planet. So those volumes are still like the foundation that VERITAS is going to give us a real leg up on. That's what excites me about Venus. I'm not really a field scientist. Right. I mostly use computers. I do things with radar instruments like VERITAS is going to fly. So I've been working for the last couple of years on a radar instrument that goes around the moon, trying to figure out how to pull the most information out of it. I do field work only as an amateur in the sense that I really love rocks, and so like I just dragged my kids to the Western United States, and we went to 4 national parks a month ago, and so that it wasn't field work; it was field vacation, and I've kind of done that in many years, but it's not really my profession. My profession is data analysis on computers. I'm in charge of looking at how craters have degraded on the surface of Venus, and thinking about the surface processes that have gone into that. This is an interesting problem because on Venus, the crater record is very different than on all the other terrestrial planets, including Earth, because the atmosphere is so thick. And also, it seems that the history of Venus is distinct from the other bodies. And on all of the other planets, the Moon, Mars, Earth, Mercury, there's big differences in the density of craters in different parts of the planet, and that's not true on Venus. We don't totally know why yet, and looking at how craters degrade is going to be one more way of attacking that problem. It's the infilling, especially, perhaps by later volcanism. So if you can figure out which craters have been flooded by volcanic eruptions in sequence, you can figure out which ones were there when the eruptions happened and which ones only post-date. And so that starts letting you slice time into sort of layers that you can pull out history from. Robbie Herrick, who's on the team, has done some already amazing work with Magellan, but the topography that VERITAS is going to give us and the radar images will really allow us to nail this question, I think. It's one of the things that excites me most about this new data. I like to give the analogy where VERITAS will take us to an understanding of Venus similar to what the Mars Global Surveyor did for the understanding of Mars after the Viking missions. It's just a transformative understanding that happens with good topography. So the big difference is the atmosphere filters the small craters out. The record on Venus is limited mostly to big craters, and there's a relatively small number of them, only of order 1,000. Whereas if you look at the moon, with the naked eye, you can easily see 1,000 craters on the moon, and there's millions that exist on the surface. Venus is special in that its crater record is sort of more limited than some of the other bodies because of this atmosphere, and that poses some challenges for understanding the geologic history. Yeah, so if I were to describe the VERITAS mission for me, it's a mission that's going to take radar and it's going to take emissivity measurements. It's going to tell us about the geology and the nature of the rocks of the whole planet and the planet's history. So those are the things that I see VERITAS as accomplishing. The day-to-day of my job is that basically I take data from spacecraft and I try to turn it into an understanding of the history of planets from that data. The way I do that is through calibrating images and radar data and then putting it into geographic information systems, GISs, like ArcMap, to place it into maps. And the placing the data into maps allows us to analyze it in spatial context and then into temporal context. We look at the history of the planet by looking at relationships between different rock units. No, the techniques that we're going to use for VERITAS, synthetic aperture radar techniques, are similar to what we do on the moon, this mini RF data that I work on. And so, no, the data type is very similar to what we've done on Venus before, and what we do on the moon, what we're going to do on Earth with the NISAR mission, and we also have done with airborne data as part of the VERITAS team. So it's not a new technique, but the data is going to be really new because it's going to be so much better than what exists. The important thing when you think about going from a football field size pixel down to like a much smaller pixel is like the amount you see goes up as like the square of that length. And so like I've been as part of Mars exploration where I looked and saw Jezero crater where the Perseverance rover is and saw it at that football scale, 100 meter per pixel. In the course of my graduate student career, we got it down to 25 centimeters per pixel. That transition from 100 meters to 25 centimeters per pixel is like incredible, right? And of course, now we're driving around as a space agency looking at the actual rocks that you can pick out in the 25 centimeter per pixel data. But like, it's an extremely exciting thing to be able to go from that, be there at that transition point. And I think that's one of the things that excites me most about VERITAS is being there when we go from the Magellan data to this incredibly improved data set, especially the topography. Topography tells you pretty much the integrated history of the sort of the forces that happen on the surface. You know, you build volcanoes, obviously with eruptions, and then on most planets those erode to some degree. There's a debate about how much erosion happens on Venus, given that it's in this thick atmosphere that doesn't have very strong winds, at pretty low speeds. And it's there's no agreement about how much sediment there is on the surface of Venus. Like maybe it's all volcanic, maybe there's some degree of small amount of dunes that exist that you can see, but that's one of the things we might really learn with new topography and images. So what I would tell a student who wants to go into understanding radar data is to take a good number of math classes first, because it's useful. You'll start seeing complex numbers in places in the real world that you may not have seen between the time you took a class with square root of negative ones in them, your geology classes. So radar data is an amazing source of insight about the planets. Yeah, so the Viper mission, which I've been intimately involved in for the last 4 years, got canceled on Wednesday. It's a good illustration of like how hard space is. Viper is supposed to be landed in a commercial landing system run by the Astrobotic company, and unfortunately their first lander didn't succeed. And so there's been a lot of questions about whether their second lander is going to be ready on time and whether flying Viper is going to be within the budget that NASA has. And so the headquarters made the difficult decision to cancel the mission this week. And that has huge emotional impact on me because I just really wanted to drive on the moon. I really wanted to do it. And so that the day-to-day can be a challenge in the space business because you could have these emotional impacts. And that sort of happened with VERITAS, right? VERITAS was in this limbo state for a long time because of budget reasons. And that was extremely challenging especially for the leadership of the team who had invested much of their life into the thing. And so that hit me this week again because of Viper. And I was just deep into it and bam. One of the things I've really learned about space missions is like the people who are doing it are incredibly emotionally invested. And I'm definitely emotionally invested in the work I do. We do our career not for money or glory or anything. It's really for just like the chance to explore and find new things out. And like so when things get canceled or delayed, it can hurt. And so you really see that, and this week has really illustrated that to me.